My name is Jimmy Torre, and I'm here to present at LambdaConf 2016. I'm going to give you a one-sided dialectic on my personal research project, which is Pervasively Reconfigurable Computing, also known as PRC. And that's how you can contact me at my usual handle, email address, PGP key, and ham radio license number. Okay, and that's the PRC. Okay, so the details of this talk is that I want to collapse the abstraction stack between machine and logical semantics. Specifically, if you have multiple, there's a genealogy, there's a lineage to languages. So C was beget in B, and then I'm pretty certain that Python is actually written in C. And if you go back to Lisp 1.5, originally it was implemented in assembly. That's why we don't have S expressions and not S expressions and M expressions. But ultimately, what happens is that a new architecture comes into play. Intel zaps us. We have to rewrite our compilers to a different backend, and then we build up this lineage again. And even below that architecture, there are the actual hardware circuits. There are the control signals, which then manipulate the hardware circuits. There's the microcode, which dispatches to the control signals. And then there's the internal assembly, reconfigurations, and all the other unknown things, which is necessary and useful in modern architectures, but not so useful if you want to actually know what you're doing with your machines. So my thesis is that a universal cell is a reversible, asynchronous, reprogrammable automaton capable of supporting binary switching logic, signal routing, and memory. Yes, in a single primitive circuit element. So in fact, it's a circuit element, but you can think of it much more like a small soft core in the same way that the transputer or the GA144, the fourth machines, or Alan Kay's idea that every single number should have its own computer or its own core associated with it. And that's what they look like. So the description of their behavior is relatively simple, but first I'm going to establish my credentials by running through a quick literature review, because I don't expect you to believe this off the top of my head. So reversible logic is bijective logic. Means that there's a one-to-one mapping, unique mapping between inputs and outputs, and you should be able to pipe the outputs back into the inputs and get the same result, or get the reverse mapped result. The reason why we like symbolic reversible logic is because it provides the basis for physically reversible logic. And physically reversible logic lets us undercut the lambda hour limit, which is the minimum amount of energy necessary to erase a bit of information. KT natural log of 2 times the number of bits you're going to erase. And where K is a constant and T is K is the gas constant and T is your current temperature. And why is this a problem? It's a problem because we're currently operating where the Landauer's limit is we're actually operating a couple order of magnitudes above Landauer's limit, but the only way that you can actually break it is to not have an AND gate or a NAND gate, which takes two highs and produces a low, and then has to shed 2 bits of energy and entropy. Also, I certainly hope that whoever's operating the video camera can hear my voice from all the way over here. And asynchronous logic is another means of, and also physics is reversible because quantum behavior is unitary evolution until it collapses. Asynchronous logic has no clock. It's different than unclocked versus a clocked signal. It only has local data flow control in the sense that operations must, if an operation is to occur, it must occur using only local information as opposed to a clock signal, which is actually an extra piece of information that lets you order your operations. And an example of a reversible logic gate is the Fredkin gate. The Fredkin gate is very simple insofar as, can I see a mouse? No mouse. Okay, well the bolded ones up there are the interesting ones. The Fredkin gate has a control line and then 2 data lines. And if the control line is 0, then the data lines just pass on through, whatever they are. If the control line is 1, then the data lines flip. And this is not only reversible, it's also parity preserving or charge preserving. Because it's parity preserving logically, it can be charge preserving electrically. And an example of an asynchronous logic gate, the classic example is the Mueller-C gate. So it has local data flow control because it only actually flips the output when it has 2 high signals or 2 low signals. If it has mixed ones, because they weren't synchronized in arriving, they weren't locally synchronized in arriving to the C gate, then it just keeps its old value. Ethos 2, reconfigurable logic, FPGAs, field programmable gate arrays, and transistor arrays. Very cool, but also very heterogeneous, logic slices and interconnect networks. So there's still a lot of It's like neurons and astrocytes in the brain, gray matter and white matter. The gray matter might actually do the reconfiguring, but the white matter is there to support it, and the white matter is doing a lot of the work and doing a lot of work behind the scenes. And we don't want that. We want all of this to be in a single, unified, homogeneous, like to use Stanislav Datskovsky's term, we want to have our computing by the pound. The transistor, okay, so transistor is up there because it is currently the queen, the crown jewel of computing. And the reason why, and I didn't actually understand this for a while, is because you can produce a single transistor NOR gate, and NOR is a universal Boolean gate. So the transistor takes a very, very small piece of physics and maps that, or allows you to map symbolic logic, sufficient for universal computation symbolic logic, onto a piece of physics. And that is ultimately the goal for this, is to now allow a bit more complicated logic, namely everything a transistor can do, but also reconfigure itself, and hopefully only employ a little bit more physics. Okay, so the two major precursors to this, although in communication with both of these precursors, they didn't think of the implications, and they also don't know anything about me, aside from the fact that I pester them on the internet, are RALA, Reconfigurable Asynchronous Logic Automata, out of MIT, from Neil Gershenfeld and David Dalrymple, primarily. And those were a tremendous insight in terms of the necessity of a stem cell, of universal cells, or of your primitive circuit elements having multiple roles or phases they pass through. Where in one phase they perform logic and processing, in another phase, and also routing, and in another phase they are subject to reconfiguration. So that is taken blatantly from RALA. They do stem cells, I do stem cells. The other part, the reversible portion, and also reversible and asynchronous, is Kenichi Morita's work with reversible logic elements with memory. And the importance of this is that it's a single operation. RLEM is not a gate, it's actually a little finite state machine that every time it performs a logical switching operation, it also performs a memory switching operation. Specifically, we have here ABC. When your memory bit is set to 1, it crosses them. And when your memory bit is set to 0, it passes them straight through. So in that sense, it also reminds me a little bit of a Fredkin gate, but with a bit of memory associated with it. A single bit of memory. Now, what is that? Yes, and it is naturally geometric. By natural geometric, I mean that you can take, usually your traces in any particular device are defined. Any particular abstract notion of a circuit, the traces are left to implementation. So if you have, yes, of course, if you have NAND, then you can build whatever you want, but you might need to have lots and lots of circuitry running, your wires running around, dumb wires. And I don't want that. I want purely homogeneous, as close to the bare metal, as close to the physical metal as possible, the physical metal as possible. And so we have, on the upper left, is an arrangement of reversible logic elements with memory, which Morita has proven to be universal. And on the right, we have my hand-drawn, hand-calculated equivalent, which does nothing more than assume that you have, so each of those intersections in the hexagonal grid is an RLEM, but instead of having 6 spikes pointing out, 3 inputs and 3 outputs, it has 3 bidirectional inputs and outputs. So it says you take the 6, you push them together, and push them together pairwise. And some of those RLEMs are left to be to perform their logic and memory operations, namely 1, 2, and 3. 1, 2, and 3 are there. Then there's bear 1 there, bear 2 there, and bear 3 in the center. And those map to 1, 2, and 3 over here. Everything else is just RLEMs in the wire phase. So we have 3 roles. We have the processing role, the wire role, and the stem role. And this demonstrates that if you could get a hexagonal array of RLEMs into this particular configuration of wires and processors, then you would have universal computation, or the potential universal computation. And that's the build order, so you can see, so you can actually trace the wires around and prove that I'm not making it up. Let's see. So so stem, processor, and wire roles. Now, the difference, there are a couple of enhancements, which I don't like that I had to do, to RLEMs to get to universal cells. RLEMs operate on an extremely bit serial model, as in, so that proof of universality is actually a proof of universality if you only ever have one control bit moving ever in your universal Turing machine. So it's actually binary logic in that there are only ever 1 and 0 charges moving through the system, but unfortunately, that means that you have to have a lot of between channel control. So if your channels are always set to 0, unless they're set to 1, then it's like having a clock because it's like always having a piece of information present. And I instead want to have within channel control. Namely, I want to be able to, given only a single wire access to a single stem cell in an array of universal cells, I want to be able to bootstrap up everything else. And to do that, you need to use your standard binary logic embedded in a ternary logic that we know from classical circuit theory, which is 0, 1, and null. So the 0 is actually a different token than the 1, and the null is the absence of a token. But it's still equivalent to the RLEM. It still follows all of the universality rules because you could just say that your everywhere null is an everywhere 0, and it's just an alpha substitution. All right, so then we have the data structure for what the universal cell looks like, the role, memory, high rail, buffer, self, mailbox. Those three are important for the stem cell only. The wire and processors only care about role, memory, input, and output. And then if you actually want to simulate it, you need to have an additional enrichment of knowing what all of your neighbors' outputs are, because this does asynchronous data flow via pull-based as opposed to a push-based model. So in a push-based model, if you push data, it's gone from your buffer, and the other side has to accept it and process it. Or the other side can send you a message saying, don't push me any data. In this case, because because there is no buffer, like so it says buffer up there, but the standard signal, which is the 0, 1, or null, doesn't get buffered along a connection between two universal cells. So you can't have any you can only have congestion within a cell. As in, there's no congestion control you can push off to registers in between, or like the wire can get filled up. The wire is not actually a wire, it's just another part of the universal cell. So each cell, when it activates, so it has its own internal timer, or rather it moves as fast as it can process data, pulls, inhales, consumes the data which is present at that point in time from its three neighbors, and that forms the neighbor output. And so the neighbor output may or may not get passed into the, so if you have neighbor output, you will not pull neighbor output if you have any output of your own, because you don't necessarily have any place to store it. And this also solves the problem of RLEMs, which for multi-stream data. So RLEMs only operate off of a single bit moving around across a matrix, whereas this lets you have multiple streams and actually converge at a single RLEM universal cell and then be dispersed. So standard signals are just 0 and 1. You never transfer around a null. A null is the absence of a signal. A stem cell can send special packets, and it can send, and so this is basically your instruction set. And the instruction set for manipulating any universal cell are composed of the elements which are in a buffer, and the buffer has two components: the target, so whether it's going to be yourself or your three neighbors, and then the command. The commands are either to become a stem cell, to become a wire cell pointing left, so rotate to the left, become a wire cell rotating to the right, processor rotating right, processor rotating left, or you can also, a stem cell might need to generate a standard signal. I actually have an extra bit, so maybe I can think if I could compress this down to 4, it'd be awesome. If not, I have an extra bit, so I can complexify it a bit more. Let's see. So it's important, and critically important, that regular, as in non-stem cells, which non-stem universal cells, can communicate with universal cells, so they can instruct the stem cells what messages they should send on. So if you have if you have a stem cell here, you don't have a chain of stem cells going all the way back to your original starting point so that you can pass on reconfiguration messages. Instead, you could have a program running over strictly standard signals that instruct a stem cell far away from your initial point of reconfiguration to build up a new circuit away from wherever your memory, the memory which prescribes the description of your local circuit is. So that's why you have both standard signals and special messages. All right. Yep. Oh, and high rail is a stem cell only listens to the first thing which talks to it. So high rail is just the piece of the neighbor which is going to send it all of its subsequent buffer input. All right, and so the last part is potential physical implementation of this. So what do we have here? We basically have a hexagonal array, but really it's a triangular array because all of the points only have three radiating spokes, and we want to permute a number of bits, which are represented by highs or lows, from one side to the other. And because it's reversible, it's going to be invertible, and so it really is taking a braid and winding and unwinding it. But it also seems like it's going to take a lot of state, because I just described a buffer that's 5 bits long, which is 32 possible states, plus input and output, and this might take lots of transistors. Rel took 10,000 transistors, but they were offering 6 different Boolean operations, and I'm only offering really one, which is switch your memory and route to the left or right, clockwise or counterclockwise. But there is a device called a circulator, which is used in radio frequency, electromagnetic frequency circuits. And it does exactly this. If you have a radio wave coming in along one of the ports, it will only be redirected to the clockwise or counterclockwise port. And in the 1960s, at the very latest, they built switchable latching iron core, magnetic ferrite core RF circulators. So I have been recently reading papers about impending VLSI-ization of waveguide circulators. I certainly hope that we can overcome the magnetic remnants problem, because now you're limited in your clock speed, not to the frequency of your signal carrier, but to the frequency which you can switch the polarity of the magnetization of the magnet inside. So I want to be an electrical engineer, but I'm not a very good electrical engineer. All right, so pathos. This is where I get to give you my argument from the heart. All this is very cool, just in the abstract sense, reconfigurable, asynchronous, reversible computing. But what I want is a computer that is a peer. And moreover, I want a computer that is an accurate representation of my understanding of the universal meta tool, which is a universal programming language, for Turing complete programming language. I envision that if I were a precocious child, my parents would give me a chunk of PRC, and that I would start playing with it and fiddling with it. And that even more so than when you're given a Commodore 64, where you can poke every single bit in memory, that I would be able to grow this and eventually build artificial intelligences which live on top of it, which can modify themselves, and have a totemic computer. That is something which is an accurate representation of me, but externalized. Or of whatever operator of the machine is, which could include the machine operating upon itself. Yes, so that's the self-hosted Bene Gesserit artificial intelligence, because Bene Gesserit could modify down to their heartbeat and the expression of hormones, and this artificial intelligence, were to be hosted on top of PRC and a universal cell array, would be able to modify itself down to the point where it would have no further dependence on any other portion of the architecture, but that of physics, and we are all ultimately limited thus far to physics. Anabasis, coming outwards from this, these are questions that I have for everyone, and also the ongoing research goals are to have possibly minimize and formalize these rules in some sort of nice theorem prover, so they don't have to do it all ad hoc. Visualization tools and tooling around it, so that I can play and build circuits that aren't just a bunch of console text output. And there's a great deal of work done in actually building more than just universal, just Turing complete primitives for this. And it's one thing to prove Turing completeness, it's another thing to actually make an efficient ALU. But fortunately, there's lots and lots of work in the reversible and asynchronous communities on doing exactly that. So I'm so enmeshed in Boolean circuit theory that when I think of what do I do when I have two numbers and I want to get their product, I think of a multiplier. But I'm certain that that is not the only way that you could do it, and I'm certain that's not the only way a genetic algorithm could figure out to do it. And epilogue, these are all the references, or most references, that inspired me. So you can go review those papers as well. Thank you.